Hi guys, this is Becky, and in this video we're going to take a look at stoichiometry and using mole ratios to solve chemistry problems. So the goals of this video are to be able to use mole ratios, to learn how to use mole ratios in solving chemistry problems, and essentially to be able to convert between substances using those ratios from those balanced chemical equations. So in class today, we talked about this idea of a mole ratio coming from our balanced equation. So if we have our balanced equation, so this is one of the ones that we looked at in class today, where we have copper sulfate reacting with ammonia or with sodium hydroxide, making copper hydroxide and sodium sulfate. So when we look at this, right, we said that the copper and the sulfate and the hydroxide react in a 1:2 ratio, and that comes from our balanced chemical equation. So for every 1 mole of copper sulfate that I have, I need 2 moles of sodium hydroxide, and I get 1 mole of copper hydroxide and 1 mole of Na2SO4, right? So I can write mole ratios here. So I know, so for a ratio that I can write would be 1 mole of copper sulfate for every 2 moles of NaOH. And I can do this between any reactant and any product, right? And when we found, when I mixed these together, that ratio gave us the most product, because when we mix them together in those ratios, all of the things react to make as much product as is possible to make, okay? This goes for all kinds of reactions, not just those that involve reactions in solutions. So like, for example, if I burn propane, which is this equation that's down here, right? When I balance my equation, I end up needing a 3 in front of that, a 4 in front of that, and then that becomes a 5 in front of the oxygen. So in this case, right, I get, so for every example, 1 mole of propane that I burn, I get 3 moles of carbon dioxide, right? And I can do this, use anything involving between any 2 reactants and any 2 products, or products and reactants, or whatever, as long as I have this balanced equation that gives me those coefficients, right? So what these are, these ratios, what they really are there a way for me to mathematically convert between substances. So for example, so like I can figure out how much CO2 I would make if I burn X amount of propane using my balanced equation. Okay, so let's take a look at that in a little bit more detail. So just as a FYI, we've done this video a little bit differently. For the rest of the video, we're going to be going through some example problems. These are in your packet where it says example stoichiometry problem. So we're starting on page 17. Okay, so we're looking at the reaction of aluminum with oxygen to form aluminum oxide. And I want to know how many moles of aluminum oxide I can form from 17 moles of aluminum. So the first step, and the first step in any stoichiometry problem, is going to be, let's start with a balanced equation. So in this case, I've given you the balanced equation, which is there below, and it's in your packet, right? Step 2 is going to be, let's make the units work. Let's make a unit plan. Before I think about any kind of numbers, let's just get the units where they need to be. So the unit that I'm starting in here is moles of aluminum, and I want to end up in moles of aluminum oxide. Now, can I go there in one step? Yeah, because I have a balanced equation that relates the moles of aluminum to the moles of aluminum oxide. So I can use my mole ratio, MR, mole ratio, to convert between moles of aluminum and moles of aluminum oxide. So what I end up with is, starting out, so now that I have a unit plan, I'm going to do my dimensional analysis. So I have 17 moles of aluminum, and I know that for every 2 moles of aluminum oxide I need to have 4 moles of aluminum. And when I put that in my calculator, I know that when I react 17 moles of aluminum, I will get 8.5 moles of aluminum oxide. All right, pretty straightforward. I have this mole ratio. I have my balanced equation, and I can use my mole ratio to convert from moles of reactant to moles of product, or vice versa between anything and anything in the equation. It gets a little bit more tricky if I'm not just talking about moles. In this case, when I'm looking at page 18 in your packets, I'm starting out in grams of magnesium and looking for moles of hydrogen gas that form when I react to magnesium with hydrochloric acid. Okay, so same thing, same stepwise process. Let's just go in a little bit more detail. I need a balanced equation here. So I'm reacting magnesium plus hydrochloric acid is HCl, and I'm getting magnesium chloride and hydrogen gas. So I end up needing a 2 in front of the HCl to balance out my equation. Okay, so I'm starting out unit-wise in grams of magnesium, and my goal unit is moles of hydrogen. Now, can I get from grams of magnesium to moles of hydrogen in one step? No, I don't know how to convert between those two. There's no conversion factor that gets me from there, but I can convert from grams of magnesium to moles of magnesium, and then I can convert from moles of magnesium to moles of hydrogen, right? So conversion factor from grams to moles. I'm going to use my molar mass or my molecular weight. Then I can use my mole ratio to convert from moles of magnesium to moles of hydrogen. Okay, so what that ends up looking like when I do my dimensional analysis is I'm going to start out with 25.0 grams of magnesium, and then, 1 mole of magnesium, so converting the grams to moles using the molar mass of magnesium from the periodic table. And then I know that from my balanced equation, for every 1 mole of hydrogen, I need 1 mole of magnesium. And then so I can put that in my calculator, and I get 1.03 moles of hydrogen. Okay, so moles of magnesium cancel, grams of magnesium cancel, and I'm left in moles of hydrogen. Okay, all right, let's try another one. I want you to try this one on your own. So in this one, we're looking for grams of carbon dioxide that are forming from the burning or combustion of 320 grams of pentane, which is C5H12. This is page 19 in your packet. Pause the video. Try this problem. Hit play when you're ready to see the solution. Okay, so in this case, we're looking for we're burning pentane. So our step 1 is our balanced equation as always. So burning pentane, C5H12, plus the oxygen. Remember, combustion is the reaction with oxygen gas, forming CO2 and H2O. Okay, I end up with a 5 in front of that, and a 6 in front of that, and that means that I need an 8 in front of the oxygen. Okay, so I have my balanced equation. Now, unit-wise, I'm going from grams of C5H12, and my goal unit is grams of CO2. I can't go from grams of C5H12 to grams of CO2 directly in one step because I don't know. Remember that these ratios are not in grams. These are mole ratios, not gram ratios. So I'm going to convert from grams to moles of pentane using the molar mass. And then from moles of pentane, I'm going to go to moles of CO2 using my mole ratio. And then from moles of CO2, I can go to grams of CO2 using my molar mass. Okay, so setting that up dimensional analysis-wise, 320 grams of C5H12. Molar mass of that turns out to be 72.17 grams per mole. So for every 1 mole, C5H12 weighs 72.17 grams. Okay, and then I know from my balanced equation that I get 5 moles of CO2 for every 1 mole of C5H12. And then I know that, because my goal unit is grams, one more, the molar mass of CO2 from the periodic table is 44.01 grams of CO2 for every 1 mole of CO2. Okay, so then when I put that in my calculator, I end up calculating in terms of significant figures that I need 975.7 grams of CO2. So if I burn 320 grams of pentane, I'm going to get 975.7 grams of CO2. Cool, right? This is just a big game, big giant game of let's get a balanced equation, let's figure out what we need to do to make the units work, and then let's do it using dimensional analysis. Okay. One more. This is on page 20 in your packets. dealing with the units that we were talking about before with respect to molarity. So in this case, we're isolating a precipitate from reacting a solution with excess sodium carbonate. And this is it's the same thing. It's just a different way to get to moles. So in this case, with our balanced equation, we're reacting silver nitrate and sodium carbonate. And we're getting silver carbonate and sodium nitrate. Right, and I need a 2 in front of that and a 2 in front of that in order to make my equation work. So unit-wise, I'm starting out in milliliters of solution, and my goal unit is mass of precipitate, so grams of silver carbonate. And we know silver carbonate is going to be our precipitate based on solubility rules. Silver compounds are not soluble unless they're nitrates, and anything else is not soluble. Okay, so I mean, again, this is the same thing. It's just I'm starting in a different unit, so I need a different path to get to moles. Well, I know the volume of solution that I have, and I know its concentration. So what I can do is go from milliliters of solution to liters of solution, right? And then from liters of solution to moles of silver nitrate using the molarity. So I can use the molarity here, and I know how many milliliters are in a liter because that's by definition. So then now I'm in moles of silver nitrate. Then from moles of silver nitrate, I can use my mole ratio to go to moles of silver carbonate. And then from moles of silver carbonate, I can go to grams. So again, same thing, just a different path. When we fill that in terms of dimensional analysis, we end up starting at 250 milliliters of silver carbonate, silver nitrate solution. Right, and then 1 liter is 10 to the third milliliters, and then 0.15 moles per liter. And now it's going to start to look very familiar, because now we can say, okay, so for 1 mole of Ag2CO3 for every 2 moles silver nitrate, and then I can use my molar mass, which happens to be 275.75 grams of silver carbonate for every 1 mole of silver carbonate. Right, and then when I put that in my calculator, I end up getting 36 grams of silver carbonate. I can only have 2 significant figures because 250, and both my concentration and volume have 2 significant figures. Okay, so 36 grams of AgNO3. Okay, so just remember that this is all a game. Stoichiometry problems and solving stoichiometry problems is a game of making the units work. Get to figure out what unit you're starting in, figure out what unit you need to be in, and how do you get from A to B using those units, right? Using units and using your molarity and mole ratios and molar masses as conversion factors to go between units. So given all of that, I would like for you to take a look at this particular problem and then bring your solution to class next time we meet. So I want you to find the mass of sodium carbonate that is necessary to precipitate out all of the calcium ions from 155 milliliters of a 0.35 molar calcium nitrate solution. Okay, give that a shot, bring your answer to class, and we'll see you next time.